Prior to 2017, the dominant approach to sequence modeling relied on recurrent neural networks. These models process data one distinct step at a time. This creates a strict mathematical constraint. To generate the hidden state for a given position, let's call it position t, the network must first complete the computation for the previous hidden state, t-1. Because the math requires the previous output to generate the current one, the architecture physically prevents parallelization across the sequence. The hardware is forced to wait for the preceding step. As sequence lengths grow, this sequential delay accumulates. The memory required to hold these linear operations soon limits batching across training examples, creating a hard computational ceiling. As long as sequence generation required sequential computation, the scale and speed of machine learning models remained restricted by their own architecture. Researchers at Google proposed a different path: dispense with recurrence and convolutions entirely. Their architecture would rely exclusively on an attention mechanism. They utilized self-attention. This is a mechanism relating different positions of a single sequence to compute a global representation, viewing the entire input simultaneously. This chart visualizes the mathematical advantage. In a recurrent layer, the minimum number of sequential operations scales linearly with the sequence length, O of n. In a self-attention layer, that requirement drops to O of 1. This constant number of operations allows every position in the sequence to be connected globally, facilitating large-scale parallel training. By replacing the time-step processing loop with global attention mapping, the transformer theoretically removed the primary structural barrier to computational scale. This diagram maps the mathematical engine, scaled dot product attention. 3 input matrices, queries, keys, and values, enter the base. The dot product of Q and K measures token compatibility. To prevent vanishing gradients, the architecture scales these products down by the square root of dk. The model then applies the softmax function to obtain a normalized set of weights and multiplies those weights by the value matrix. Instead of looping through data sequentially, this sequence of matrix multiplications calculates the exact contextual relationship between any two tokens in the entire sequence. A single attention function has a limitation. Averaging the results inhibits the model's ability to attend to information from different representation subspaces at different positions. Looking at this multi-head attention diagram, we see the structural solution. The model runs multiple attention layers in parallel. The original query, key, and value matrices are linearly projected 8 separate times. These parallel heads process simultaneously, then concatenate into a final weight matrix. Because the dimensionality of each head is reduced, the total computational cost matches single-head attention, but it allows the network to capture diverse syntactic and semantic structures simultaneously. This architecture diagram details the full framework, relying on 6 identical stacked layers. The encoder, on the left, contains a multi-head self-attention layer and a feed-forward network, bridged by residual connections to maintain information flow. The decoder stack operates autoregressively. When generating the next token, it consumes its previously generated symbols as additional input. It uses a third sublayer to perform multi-head attention over the encoder's final output. To maintain causality, a masked self-attention layer blocks leftward information flow by setting future connections to negative infinity right before the softmax function. This unified stack allows every position to contextually evaluate the entire input sequence simultaneously, while strictly enforcing causality during the output generation. Discarding recurrence introduces a paradox. Without a linear sequence, the system receives all tokens at once. It has no inherent concept of order. To inject the relative and absolute position of the tokens back into the math, the authors use positional encodings. The model calculates sine and cosine functions at different frequencies. Wavelengths form a geometric progression from 2π to 10,000 times 2π, generating unique positional vectors for every point. These vectors are then directly summed with the input embeddings before entering the stacks. Positional encodings solves the final hurdle. Data is processed in parallel, yet sequence order is strictly maintained. The researchers tested this architecture on the standard WMT 2014 English to German machine translation task. This chart maps the empirical results. The Transformer BIG model established a state-of-the-art BLEU score of 28.4, improving over existing best results, including heavily engineered legacy ensembles, by more than 2 full points. More importantly, it achieved this record score in exactly 3.5 days of training on 8 P100 GPUs. This was a fraction of the floating point operations required to train competitive recurrent models. The empirical data was decisive. Discarding recurrent complexity for raw parallel attention proved mathematically and computationally efficient. The paper concludes with a vision to extend this sequence-agnostic architecture far beyond text. By utilizing restricted attention mechanisms, the model can consider isolated neighborhoods of input data, allowing it to handle high-resolution images, audio, and video streams. The engineering victory lies in the abstraction. The authors effectively separated the act of understanding a sequence from the act of computing it sequentially. By bypassing the LSTM sequential bottleneck, the transformer provided the architectural framework that supports modern, large-scale foundational machine learning.